Simple mixtures are an essential part of chemistry and can be understood by examining how their physical properties depend on composition. The thermodynamic description of mixtures introduces partial molar quantities and chemical potential, which describe how the properties of a mixture change when the amount of one component changes. Experimental relationships such as Raoult's law and Henry's law help describe the behavior of components in mixtures and solutions. The topic also covers the properties of solutions, including vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure, as well as deviations from ideal behavior through the concept of activity. Now that we have introduced the thermodynamic description of mixtures, we need to develop a way to describe how the properties of a mixture change when we add one component to the mixture. For a pure substance, quantities such as volume, enthalpy, and Gibbs free energy are relatively straightforward. If we have 1 mole of pure water at a specific temperature and pressure, its molar volume is simply the volume occupied by that 1 mole of water. However, things become more interesting when we form a mixture. In a mixture, the properties of one component are influenced by the presence of all the other components. Water molecules in pure water are surrounded almost exclusively by other water molecules. But water molecules in an ethanol-water mixture may be surrounded by ethanol molecules as well as water molecules. Because the molecular environment is different, the contribution that 1 mole of water makes to the total volume of the mixture can also be different. This idea leads us to the concept of a partial molar quantity. The most familiar example of a partial molar quantity is the partial molar volume. The partial molar volume of component J is the change in the total volume of the mixture when 1 mole of J is added, while temperature, pressure, and the amount of all other components are kept constant. Let's apply this idea to the example shown on the slide. Consider a large quantity of pure water. Suppose we add 1 mole of water to it. At room temperature, the molar volume of liquid water is approximately 18.02 cubic centimeters per mole. Therefore, when 1 mole of water is added to a large amount of pure water, the total volume increases by 18.02 cubic centimeters. So the molar volume of pure water under these conditions is 18.02 cubic centimeters per mole. Now, let's consider the second example on the slide. Suppose that we have large quantity of pure ethanol and we add 1 mole of water. You might initially expect the volume to increase by 18.02 cubic centimeters because that is the molar volume of pure water. But experimentally, the volume increases by only 14.00 cubic centimeters. This implies that the partial molar volume of water in ethanol is 14.00 cubic centimeters per mole. Why? Because the volume occupied by molecules depends on their molecular environment. At the molecular level, molecules do not simply occupy rigid boxes of fixed volume. The interactions between molecules determine how closely the molecules can approach one another and how the liquid structure is organized. Water molecules have strong intermolecular interactions, particularly hydrogen bonding. Ethanol molecules can also hydrogen bond with water, but their molecular structure is different. Ethanol contains a polar hydroxyl group attached to a nonpolar ethyl group. Consequently, when water molecules are introduced into ethanol, the interactions between water and ethanol molecules can produce a molecular arrangement that is different from the arrangement in pure water. As a result, the total volume of a mixture is not necessarily equal to the sum of the volumes of the pure components. This is the fundamental reason why we need partial molar quantities. The word partial emphasizes that we are considering the contribution of one component in a mixture, while all the other components are held constant. Let's look more carefully at the concept of partial molar volume. In the previous slide, we introduced the idea that the volume contributed by a substance in a mixture is not necessarily the same as its molar volume in the pure state. This slide gives us more rigorous mathematical definition and importantly shows us how to interpret partial molar volume graphically. Consider a mixture containing several substances. Let capital V represent the total volume of the mixture and let n sub j represent the number of moles of component j. The partial molar volume of component j, denoted by V sub j, is the first partial derivative with respect to n sub j. N prime represents the amount of all the other substances in the mixture, which are held constant. It represents the change in the total volume of the mixture per mole of J added, while temperature, pressure, and the amount of all other components remain constant. There are several important details in this definition. First, we are looking at a change in total volume, not the volume of component J by itself. Second, we change only n sub j. The amounts of all the other components are held constant. Third, both temperature and pressure are constant. And finally, because this is a partial derivative, we are considering an infinitesimally small change in the amount of J. This is illustrated in the graph in the upper right portion of the slide. Here, the vertical axis represents the total volume, capital V, and the horizontal axis represents the number of moles of component J. Temperature, pressure, and the amounts of all the other components are held constant. Notice that the curve is not a straight line. Instead, it has a changing slope. The partial molar volume is the slope of this curve. So, if we choose a particular composition corresponding to point A, the partial molar volume of J is the slope of the tangent line at A. Likewise, at point B, the partial molar volume is the slope of the tangent line at B. The slopes at A and B are different. This implies that partial molar volume varies with composition. Now, imagine adding water to ethanol. The water molecules are surrounded by a very different molecular environment involving both water-to-water and water-to-ethanol interactions. As we continue changing the composition, the molecular environment surrounding the water molecules changes continuously. Consequently, the incremental contribution of water to the total volume also changes. This is why we cannot assign one universal value of partial molar volume to water. As you can see the negative slope at point B, the partial molar volume can be negative. This can occur when the interactions between the molecules produce a sufficiently strong contraction of the mixture. Note that a negative partial molar volume does not mean that the substance itself has a negative physical volume. It implies that adding that component to the mixture produces a net decrease in the total volume. Suppose we have a binary mixture containing components A and B. The change in the total volume, dV, can be expressed in terms of the partial molar volumes of A and B. The three-dimensional diagram in the lower right corner provides another way to visualize the concept that the change in the total volume of the mixture is the sum of the incremental contributions from each component. The vertical axis represents the total volume, capital V. One horizontal direction represents the number of moles of component A, and the other horizontal direction represents the number of moles of component B. Every point on this three-dimensional surface corresponds to a particular mixture composition and its associated total volume under conditions of constant pressure and temperature. Imagine that we stand at a particular point on the surface and then move along the surface in the n sub A direction while keeping n sub B fixed at C. We are effectively taking a cross-section of the three-dimensional surface. This means that at a fixed amount of component B, the total volume changes as the amount of A changes. The slope of the tangent line at any point on this curve represents the partial molar volume of A. The change in the total volume can be written as shown here under conditions of constant pressure, temperature, and the moles of B. Now, consider fixing the amount of component A fixed at D and examine how the total volume changes as the amount of component B changes. The slope of the tangent line at any point on this curve represents the partial molar volume of B. The change in the total volume can be written as shown here under conditions of constant pressure, temperature, and the moles of A. Now, suppose the amounts of both A and B are changing. Then, the change in the total volume can be written as shown here. Since the two slopes in the equation represent partial molar volumes of A and B, respectively, this equation can be simplified like this. Now that we have discussed partial molar volume, we can extend the same concept to another thermodynamic property, partial molar Gibbs energy. The partial molar Gibbs energy of a substance J in a mixture is called the chemical potential of J, denoted by mu sub J. The chemical potential mu sub J is expressed as the first partial derivative of the Gibbs energy with respect to the number of moles of J, while the temperature, pressure, and the amounts of all other components remain constant. As you can see from the mathematical expression for chemical potential, the chemical potential tells us how the Gibbs energy of a system changes when a small amount of a particular component is added, while the temperature, pressure, and the amounts of all other components are held constant. Suppose we have a binary mixture containing A and B. The Gibbs energy is a function of temperature, pressure, and the amounts of the two components. Therefore, the total differential of the Gibbs energy can be written as shown here. Under constant temperature and pressure, the total differential can be reduced like this by eliminating the first two terms. Since the first partial molar Gibbs energy of a component is the chemical potential of the component, this equation can be simplified as shown here. The Gibbs energy of a mixture can be found by integrating both sides of the equation. Mu sub A and mu sub B can be treated as constants when the changes in their values are negligible, as the composition of the mixture changes over a narrow range. So, mu sub A and mu sub B can be brought out of the integral. This leads to G equals mu A Na plus mu B Nb. In Chapter 2, the exact differential for Gibbs energy can be written dG equals negative SdT plus VdP. However, for a binary mixture that is made of A and B, the Gibbs energy also depends on the composition, and as a result, we should include these two terms in the equation, mu A dNA and mu B dNB. This equation is called fundamental equation of chemical thermodynamics. At constant temperature and pressure, dG is equal to mu A dNA plus mu b dNb, which represents the maximum non-expansion work that can be obtained from the system with the appropriate sign convention. This implies that non-expansion work can arise from changes in the composition of a system. One important example is an electrochemical cell, where a chemical reaction takes place. The electrical work performed by the cell can be traced to the change in composition as products are formed from reactants. Now that we have defined chemical potential as the partial molar Gibbs energy, I want to take a step back and explain why chemical potential is such a central concept in chemistry. The chemical potential of component J in a mixture is described as the change in Gibbs energy of the mixture when we add a small amount of component J to the mixture while keeping temperature, pressure, and the amounts of all other components constant. But chemical potential is actually much more important than simply being a convenient definition based on Gibbs energy. Chemical potential appears naturally in the differential expressions for all of the major thermodynamic potentials, such as internal energy, enthalpy, Gibbs energy, and Helmholtz energy. It tells us how the thermodynamic state of a system responds to a change in composition, regardless of which thermodynamic potential we choose to use. Let's begin with the equation we have already discussed for a multi-component system. Gibbs energy is defined as H minus Ts, and H is defined as U plus PV. Plug this into the equation for capital G. Now, G can be expressed as U plus PV minus Ts. We can rearrange this expression to obtain U equals G minus PV plus Ts. Taking the differential of both sides of this equation gives us this expression. Replace dG with the expression for dG shown at the top. SdT and VdP terms cancel out. Now we are left with du equals Tds minus Pdv plus mu A dNA plus mu B dNb plus etc. This is the generalized equation for internal energy of a system whose composition may change. This equation can be modified for a binary mixture as shown here. At constant entropy and volume, the internal energy is a function of the amounts of A and B. Therefore, the differential of internal energy under these conditions is reduced to mu A dNA plus mu B dNb. The total differential of internal energy can be written as shown here. By comparing these two equations, we can identify chemical potential of component J as rounded du over rounded dnj at constant S, V, and n prime. Likewise, the same chemical potential also appears in the fundamental equation for enthalpy and Helmholtz energy. This shows that chemical potential describes how the major thermodynamic properties such as internal energy, enthalpy, Gibbs energy, and Helmholtz energy depend on the composition of a system. This is why chemical potential plays a central role in chemistry.